At Tesla's much-talked-about Battery Day, Elon Musk made one of those bold remarks that left the audience divided between excitement and skepticism. He said, "There are batteries in limited production right now that do exceed 400 watt-hours per kilogram, which I think is about the number you need for decent-range, medium-range aircraft." For many, it sounded like yet another example of Musk's typical futuristic promises, ambitious, visionary, but possibly too far-fetched to be grounded in reality. Critics rolled their eyes, dismissing it as Tesla's public relations showmanship. Yet here we are, nearly 5 years later, and those words are beginning to prove themselves not as exaggerations, but as the outlines of a carefully crafted roadmap. What seemed like hype is gradually crystallizing into a tangible possibility. The Tesla superelectric plane, a bold attempt to redefine how aviation works by turning those high-density batteries into real hardware capable of offering around 400 miles of range and turnaround times of only about 12 minutes. The concept may sound radical at first glance, but when we peel back the layers of technology and design, the project begins to look not only plausible, but potentially transformative. This aircraft is not just a vision sketched on a whiteboard. It is being imagined with a set of integrated technologies that address the biggest challenges electric aviation faces: drag reduction, propulsion efficiency, battery swapping and cooling, and fast passenger turnaround. To understand how the Tesla superelectric plane could work day after day, we need to explore its design in depth, from the composite airframe and distributed propulsion system to its modular batteries and clever cabin design. Let's break it down into its defining features. One of the most fundamental aspects of the Tesla superelectric plane is its exterior design, which is carefully tailored to achieve efficiency at every level. The aircraft is expected to use a one-piece composite skin, dramatically reducing the need for joints, rivets, and seams. Why does this matter? In aerodynamics, every rivet and gap creates tiny disruptions in airflow that accumulate into drag. By eliminating many of those imperfections, Tesla's design creates a surface that is flatter and smoother, allowing air to pass over it with less resistance. On top of that, a hydrophobic nanocoating is applied. This coating resists dust, rainwater, and other contaminants, ensuring the aircraft maintains its aerodynamic cleanliness even in adverse weather. The result is a significant reduction in skin friction drag, which typically accounts for 40 to 50% of the parasite drag on small to mid-size aircraft. Even a small drop in friction coefficients, just a few percentage points, translates into meaningful reductions in drag, which in turn allows the aircraft to fly farther on the same amount of stored energy. But the improvements don't stop at the fuselage surface. The Tesla superelectric plane incorporates long, slender wings with winglets, another deliberate choice to reduce drag. As wings get longer relative to their width, a higher aspect ratio, they produce less induced drag, which is a drag caused by the creation of vortices at the wingtips. A typical increase in aspect ratio from 10 to 14 could reduce induced drag by nearly 30%. Add in the winglets, small vertical extensions at the wingtips, and you achieve yet another incremental reduction of 5 to 10%. Together, these changes substantially cut the energy required to keep the plane cruising efficiently. The designers also address drag caused by the landing gear. Instead of leaving wheels and struts partially exposed to the airflow, the Tesla plane's gear retracts into sealed bays with flush doors, ensuring the underbelly is as smooth as possible. On traditional planes, unsealed gear can add several percentage points to drag, but Tesla's design eliminates that penalty. Even seemingly minor details have been refined. Flush-mounted maintenance panels, antennas, and ducts minimize surface protrusions that could otherwise act like miniature bricks in the airstream, each creating localized turbulence. Taken together, these exterior innovations may reduce total drag by several percentage points. For a battery-powered aircraft, where energy reserves are far less forgiving than those in fossil fuel tanks, every single percent of drag reduction is invaluable. Moving on, let's talk about one of the most revolutionary aspects of this aircraft: distributed electric propulsion. Unlike traditional aircraft that rely on one or two massive jet engines, Tesla's design places multiple smaller electric motors along the wing. Each motor drives a variable pitch propeller, and together they distribute thrust more evenly across the wing surface. This setup produces several cascading benefits. For takeoff and landing, The blown airflow over the wing generates more lift, allowing the plane to use smaller wings without sacrificing safety. Smaller wings mean less wetted area, and therefore less drag during cruise. During mid-flight, distributing thrust also reduces the risk of asymmetric pull in the event one motor fails, improving safety. The efficiency of the propulsion system is another highlight. Inverters typically achieve around 98% efficiency, motors around 94 to 97%, and propellers 80 to 88%, resulting in an overall system efficiency of 74 to 83%. By splitting thrust across many smaller motors, each propeller operates closer to its optimal range, nudging that overall efficiency a few points higher. Those few points, in an electric aircraft, can be the difference between viable range and impractical limitations. Moreover, Tesla's design incorporates direct drive systems, eliminating gearboxes altogether. Gearboxes normally introduce mechanical losses and require extensive maintenance. By cutting them out, Tesla not only improves efficiency by 2 to 5%, but also reduces long-term upkeep. Another clever element is regenerative braking during descent. Much like Tesla cars, the electric plane can allow its propellers to windmill in controlled conditions, recovering a small portion of energy, perhaps 1 to 3% of the total flight's energy demand. While that might sound negligible, it is enough to power auxiliary systems and reduce strain on the main battery during landing. The regenerative effect also lessens the load on mechanical brakes, extending the lifespan of landing gear components. And when it comes to reliability, the distributed propulsion layout offers redundancy. If 1 out of 12 motors fails, the aircraft can adjust thrust distribution and still fly safely. Each motor is contained in a modular pod that can be swapped out within an hour, dramatically reducing downtime and keeping fleet availability above 99% when spares are stocked. Of course, none of this matters unless the battery challenge is solved, and Tesla's engineers are tackling that with cassette-style belly batteries. These packs slide in and out on rails beneath the fuselage, much like swapping a battery in a large power tool. A megawatt-hour pack weighing around 3.5 to 4 tons can be removed and replaced in under 10 minutes with specialized ground equipment. That means the plane does not have to wait around to charge. Instead, it can swap in a fresh, pre-charged pack and continue flying almost immediately. For operators who prefer charging instead of swapping, the plane supports ultra-fast nose charging at 1,000 to 1,500 volts. With liquid cooling integrated into the packs, Tesla's system can handle the immense thermal load, hundreds of kilowatts of waste heat, generated during fast charging. Automated safety checks, completed in less than a minute, ensure that the aircraft never compromises on safety while still maintaining speed and efficiency. Finally, the passenger cabin design addresses one of the most overlooked causes of delay in aviation: boarding, deboarding, and cleaning. Tesla's cabin uses dual doors in a straight, low-floor aisle to allow passengers to board and exit simultaneously, cutting down bottlenecks. Studies show 2 doors can reduce boarding time by nearly 9%, and when combined with optimized strategies, the improvement can reach 25%. Lightweight seats, constructed from aluminum and composites, further reduce overall aircraft weight while being easier to clean. By using smooth, soil-resistant upholstery and minimizing dust-collecting details, Tesla aims for quick cleaning cycles of 6 to 10 minutes, far shorter than the industry average of 15 to 25 minutes. Even baggage storage is redesigned. More carry-on space under seats reduces the need for passengers to wrestle with heavy overhead bins, speeding up aisle flow while simultaneously cutting structural weight. Quick-release panels allow fast maintenance and replacement of high-wear interior parts, meaning the aircraft spends less time grounded. When all these elements are viewed together, the Tesla super-electric plane starts to feel less like a fantasy and more like an engineering blueprint in motion. A smoother exterior reduces drag and boosts range. Distributed electric propulsion improves efficiency, safety, and maintenance cycles. Cassette-style batteries enable rapid turnarounds that rival the pit stops of Formula One racing. And a smartly designed passenger cabin minimizes downtime on the ground. The sum of these innovations is a plane capable of delivering a 400-mile range and turnaround times of roughly 12 minutes, a feat that could redefine regional air travel. From the nano-coated skin to the modular cabin, Every decision points in the same direction, making electric aviation not just possible, but practical. For skeptics who once rolled their eyes at Musk's Battery Day remark, the emerging reality suggests otherwise. What once sounded like hype may very well be the beginning of an aviation revolution.